For today, I'm afraid I'm going to end up doing a fair amount of talking about optics. We're not going to get too much of that through most of the course. A lot of the course will be about ideas and what's been going on, but I think this material is probably important for understanding how the microscope developed and what it became useful for. There's also some interesting history. So I want to start by reviewing the basic ideas of how you form an image in a microscope. And this is really as simple as possible. And so let's go for it. The important thing to know about, first of all, is that if you have a simple convex lens like this, that lens has what's called a focal point. And the focal point is defined as the spot to which parallel rays of light are brought. So if you have light traveling, and I'll take one point here, say on this object, that's traveling parallel to the axis, like this, that ray of light will eventually be focused through the focal point, through this spot called the focal point. And so that's a rule you can use when you're trying to figure out how images are formed. So the other part of that is that rays of light that pass through the center of a perfect lens, that's a peculiar concept, okay? But if they pass through the center of a perfect lens, they travel without being bent, without changing their path. So they go straight, and the light that was traveling parallel goes through the focal point. And then what happens is when those rays of light converge into a spot, like here, that ends up recreating in space the same area, sort of, that was your object itself, except in this case, it turns out to be upside down. But this is an image of that same spot that started here. So we could continue this and make the diagram impossibly complicated by extending it to all the rays that come out from everywhere on this arrow. But we'll just extrapolate it and say that then what we end up with is an image in space of that arrow like this, sitting in space. And if we put a screen or a piece of paper in front of that, we'd see it. You'd see it in space. So that's a perfect lens. But what we discovered, we talked about earlier in the class, is that we don't get these perfect lenses, that in fact, there were two major kinds of distortions that showed up during the 17th century. And what I want to talk about today is a little bit about how we got to correct for those distortions. So here's a very nice summary page with a link for you to find out, if you want, where this information is, so it's available for you. And so there are these two types of aberration. The simple one we've talked about a bunch of times, which is chromatic aberration, where the idea is that, and I'll give you another diagram of it in a moment, that rays of light of different wavelengths, like this one, which is the blue, and this one, which is the red, are refracted slightly differently by most lenses, by a simple glass lens, okay? And it's the process which is called dispersion. And that's what basically what Newton saw when he put light through a prism. When you put light through a prism, then it separates the light. So here's a prism. It's very hard for me to draw white light on a screen like this, but let's assume this is white light. it enters the prism, and then different wavelengths are refracted to different extent. So this would be, let's say, the red goes out here, and the blue goes out here. And the rest of the spectrum is spread out throughout that, okay? Normally, those distances are much smaller than what I've shown here. Even here, this is sort of what you get. And the end result of that is shown in these pictures over here, sort of. These pictures are not as good as the ones I showed earlier in the year. But basically, the idea is that there's a red fringe here over on this side and a blue fringe on that side. And it's only if you can somehow bring them together that you can get a much sharper image like this one. Okay, that's chromatic aberration. The other aberration is this thing called spherical aberration. And in a certain way, it's almost misleadingly named, because it isn't that it creates a sphere on your image. I mean, if you look at this uncorrected image, it doesn't look at all as if it's been distorted by a sphere. It's just that it's out of focus. And the reason that that's called spherical aberration is that it has to do with the fact that light, when I told you that light rays entering the lens parallel all go through the focal point, I lied. So the light rays that are parallel close to the center, close to the axis, go through the focal point, but the ones at the edge of the lens tend to go slightly off. So let's go back to this diagram. And you'll see the idea here is, here's light coming in at the edge of the lens, and it's a little hard to follow. Let me draw the line. Goes sort of here, and then continues on, where the light from the center of the lens, or towards the middle of the lens, tends to go more out towards the edge. The end result of that is that instead of being brought together at a single point, the light rays are brought together in a kind of a smear, like this. And so no matter how much you try to get the image in focus, all you do is you focus a little bit more or a little bit less on that smear until you figure out a way to correct for spherical aberration. So now we go into a little bit of history. First, this is my kind of simple-minded way of trying to show how the correction is done. And the answer turns out that different types of glass, so I'm going to say this is some sort of flint glass, I'll give it an F. And the other type of glass, which I'll call a quartz-based glass, Q. If I make prisms of exactly the same size, in the same angles, and pass light through them, what will happen is that the distribution of wavelengths, which will be the same from each one, but the size of this from here to here, size of the fan, if you will, that is the distance to which they're refracted, will be different. So the idea is that this one is smaller and this one is larger. So that was an observation that was made somewhere around the early part of the 18th century, actually, 1729, 1725, something like that. And a man by the name of Hall figured out that if I make two lenses, if he puts together two lenses, and you take one of them and instead of making it a convex lens, you make it a concave lens, so it goes in like this. Then what we have is, this is my inverted pattern of these things. So that what happens is that if you now follow, say, the red light that comes out of a beam of light that goes through this concave lens, it's refracted to a certain extent, and then it goes through the convex lens and it's refracted in the other direction. Now, the interesting part about this is that the magnification that you get out of a combination of lenses like that, because they're different strengths, because of the way you set it up, will bring all of the light together to a point. And so that point will have the red light and the blue light brought together to the same spot. And what that does essentially is it corrects for the chromatic change by balancing these two lenses together. Ultimately, that only balances the red and the blue. So what you actually have to do is put in some more lenses that will compensate as well for the green light, and then you get even better correction for your sample. So here's the story. This is a wonderful bit of story. Originally, this correction was figured out, as I said, somewhere in the 1730s, 1729. And it was developed by a man named Chester Moore Hall. The interesting thing, trivial interesting thing, is that his middle name is spelled either Moore, let me write it out for you. It's either Chester Moore Hall or Moore Hall, or so looking up this man to try to get some information about him turns out to drive all the search engines crazy. And it turns out there just isn't an awful lot about him. So what he was basically an optician, and he realized that for telescopes where the lenses were pretty large, you could actually make this kind of lens in which you could create a double lens in which one type of glass would be a concave lens and the other would be a convex lens. Now, Moore, it turns out, was a little paranoid. And so what he did was he got in touch with two separate lens grinders and asked one to make the concave lens and one to make a convex lens. So he had two manufacturers, two other opticians grinding these lenses for him. It turns out both of them subcontracted it to yet another optician, man by the name of George Bass. And Bass figured out what was going on. So that's this little point over here. Okay, so Bass figured it out and got in touch with Moore and said, I know what you're doing. Okay, let's work together, but let's not tell anyone else about this system. So this is somewhere around 1733, and this secret design was developed. Then it depends on which story you read. This is the one I got from Guy Cox, and Guy Cox is a wonderful man in Australia who's done wonderful things for teaching optics and running microscope labs. He's around, he's still around, and a very active and very interesting man. So he wrote this for the New Scientist as a letter in response to something that had been submitted about the history. And so these paragraphs come from what Cox had written. What he didn't report, and this is somewhat apocryphal, we don't know for sure if this really happened. What he says is 20 years later, John Toland, who was also interested in developing telescopes and for these purposes, wanted to create an achromatic telescope. But for other reasons, he walked into Bass's shop and he was looking for a reading glass. This is the story. And he picked one out and Bass said, you know, if you take this other glass, it gives you a much better color reading. The colors show up very differently. And supposedly, this triggered Toland to realize, wait a minute, you could take these two glasses, put them together, and create, again, a corrected lens. So Toland, it's a T, it should be, okay? John Toland worked, again, the spelling of these things is all very tricky. Anyway, this man, John Toland, got to work with Bass and made some more lenses, okay, eventually. But he, Toland, and I'll get the spelling corrected by the end of the day, okay, apparently patented this design. So Hall apparently didn't care. Hall hadn't really been too concerned about what happened once the lenses were made. Apparently, Hall lost interest in all of this, having made these interesting lenses. So Toland patented it in 1758 or so. A little bit later, man, actually his name was Ramsden, whose name is not in here. Ramsden wanted to use the same sort of lens design and scopes that he was building, and discovered that there was this patent. And so he sued Toland to see if he could free up this patent so he didn't have to pay Toland, you know, a commission every time he made a lens. And so they sued it, he sued it, and the end result of the suit turned out to be a very interesting one, in that the judge finally said that although it was clear that Hall had priority on this lens, since he really wasn't doing anything with it, the phrase from the judge is, if you leave it in your desk drawer, nobody cares about it and it's not being used, therefore you've given up some right to it. This would be a very interesting thing to have these days as a suit. So that basically Toland deserved the patent protection for bringing the idea to market. And so those achromatic telescopes were available since then. And there's still things you can find if you're interested in antiques. The problem that they ran into was that if you now try to do this thing for a microscope, it turns out to be a much bigger deal, because now instead of a lens structure that, oh, maybe looks like this, I'll draw a kind of a version of this thing, if you will, that fits in a telescope. So this is something that's, I'll use centimeters. You know, this could be 15, 20 centimeters across from here. Quite a few inches to make a telescope. When you want to make the same sort of thing for a microscope, now you want something that's a fraction of a millimeter. And what becomes important now is that the difference in refraction, because this curvature is now so large, the effect of spherical aberration, here's the spherical aberration effect. Well, you have to assume I've really scribbled that, but that this spherical aberration effect is really pronounced, is huge. So now we have to move forward about 70 years, interestingly enough, to a man by the name of Joseph Jackson Lister. See, where is his name? Here. Once again, this is a little tricky to find out about because Joseph Jackson Lister had a son named Joseph Lister. And Joseph Lister, the son, is famous as a surgeon, known for actually developing the whole idea of antiseptic surgery, of asepsis. So he developed the use of carbolic acid as a way of sterilizing the environment. And that's why when you hear about old-fashioned surgeries or wartime surgeries, there's always some comment about the smell of carbolic being a problem. Well, one more side issue on this Lister as a surgeon. Man in the United States named Lawrence, probably also Joseph, I think, Lawrence. You don't need to know this, but it's just cool again. Developed his own antiseptic solution, mostly to use as a mouthwash. And in honor of Lister, he called it Listerine. Oh my gosh. So that's the history of where Listerine comes from as a common product around here. Well, Joseph Jackson Lister, the father in all of this, started out by inheriting his parents, joining his parents' wine business, and stayed involved with the wine business throughout, being quite successful. But as he did, he clearly had some interest in microscopy. He developed the interest in microscopy. He picked up achromatic lenses for the microscope from many different people, including, as it turns out, Robert Brown. We'll get to Brown again a little later. But he picked up these achromatic lenses and discovered that they really did have very, very serious spherical aberration. And so he began to make his own lenses, and he worked through these things and discovered an interesting phenomenon, which I'm showing you here on the left, that comes from a Wikipedia page, mostly on the physics of spherical aberration. And what turns out, what J.J.Lister, I don't know what to do. By the way, Lister, the surgeon, had a son who was also named Joseph. And he wrote a history of his father and his grandfather. So the names will drive you crazy eventually. At any rate, what Joseph Jackson Lister showed is that if you shine a beam of light into one of these achromatically corrected lenses, okay? This is the achromatic doublet type of lens. When you shine a beam of light in and bring it to a focus, interestingly enough, it's often that the light is somehow overcompensated and is brighter on one side of the focus than on the other. And if you change the position of that light, so it's further away from the lens or closer to the lens, you can change the amount of compensation so that in this first case, there's a kind of an overshoot. And if you hold the light in a different position, you get an undershoot. And so what Lister realized is that it's possible if you take two lenses, two pairs of lenses like this. Now you're going to see a little bit of a small amount of magic here. That if you adjust the position of two lenses, one with respect to the other, you can get it so that they compensate the overshoot from the undershoot, like this. And then what you end up with, as you might expect, is light that's actually brought to a sharp focus. The term for this kind of lens is aplanatic, which means it's basically corrected for spherical aberration. Well, he started working on this. He actually formed a company to make microscopes, working with someone else, a man by the name of Ross. You don't need to keep all these names in your head. And they discovered that sometimes the correction was good when they looked at samples, and sometimes it wasn't. And it turned out that the difference had to do with the cover slip that they were using, the thickness of the cover slip, or whatever the glass was above the sample. And they realized that what you have to do then is develop a system. Now I've got to do one more bit of magic here. You could adjust the position of that aplanatic focus, if you will, the aplanatic spot, by adjusting one of the lenses in the system. So people actually made microscopes. There are some designs for microscopes in which the objective lens looked sort of like this. There was an objective lens with an achromatic lens in there. Here's an achromat. Okay, and so this was the lens. And then they put a separate barrel around that one with another lens mounted in it. In the original design, what they would do is they'd put these two together like that and then lock it in place. Later on, because of this cover slip thing, they discovered that, well, maybe we should keep it loose and slide that lens up and down. But that turned out to be a big problem, because if you slid it down too far, you'd break the cover slip and possibly shatter the lens you were looking at. So what people came up with, and I'll give you a wonderful diagram of that in a moment, but I'll just quickly draw it here. They designed a lens where here's the barrel now, and then there would be one achromatic lens here, another achromatic lens here. And remember, if you wanted to correct all the wavelengths, you'd have to actually add generally a third achromatic lens. And then one more lens in the middle that was adjustable. The mechanics of how to adjust that lens, of course, is quite a challenge, but the people designing these lenses were really quite impressive. So here's an example of that. And this is a way of actually seeing in this example that I'll run up as part of a demonstration that you'll see in a minute. This is one of these complicated lenses here. You see, and it has several different components, a front lens and another. But what's important to see is that there's actually built into this lens a movable lens group, okay? Now let me bring up the website that has this active demonstration in it. So this is a demonstration from something called Microscopy U, which is a derivative of the original Microscopy website. But it has this, here you can see the movable lens group. And here you can see something that should be in focus. I think I'm going to change the sample. There are lots of samples. I'm going to put this so you can play this game yourself. Let's try this tick mouth image, okay? And so I'll bring it into focus first. And I can get it in what looks like pretty good focus here, right? But then if I adjust, watch the moving lens as I move this. It gets even sharper in focus, and then I can reuse this lens to bring it even further in focus. Let's pick another one where it's even more obvious. Okay, I'm going to take the movable lens and slide it all the way out. And now you'll see that as I try to bring it in focus, I get close, but not good enough. And that's because of spherical aberration in the system. Now, if I change the position of the middle lens, and you can see it moving, I hope, I get to a point where the image is a lot sharper, and then maybe I can refine the focus even more and get even more of an image. Okay. And just for the fun of it, one more, which is a fluorescence image. It's a fluorescence image of neurons. And you can see I'm getting close to focus, but no, not really great. Then I can adjust this color to where it looks a little bit better. And then see if now I can get even sharper focus here. Now, what's interesting in terms of modern microscopy, 2 points. First of all, this correction is in terms of thickness of cover slip, okay? And you'll see you get microscope cover slips that are given numbers, number 1, number 2, number 3, number 1.5. Those more or less correspond to the thickness of the cover slip. And for some purposes, you might want to use something like a 0.2 or 0.25, a thicker cover slip, because you've got some kind of heavy sample. For other purposes, you might want a very thin cover slip because your sample itself is very thin and you want to get very close to the sample. And then it turns out that the standard cover slip thickness turns out to be about 1.5 or 0.15. Obviously, for this particular image, that's not useful at all, but let's see if there's one where it might make a difference. See if I can bring this into focus. This is a phase contrast image. And actually, you see that this is a little bit thicker than usual. Okay. Now, let me go back to the basic page here and point out that you might have a sample sitting on a slide. That's supposed to be a glass slide. Okay. And you have a sample of some sort on here. And then you have a cover slip. Not only do you have a cover slip to think about, but you also have the liquid in which this sample is embedded. So the light that's coming to your microscope is your microscope lens. Remembering that there are many of these lenses up here, that light is passing through several different layers of refractive index, which is what you're really looking at here. And those refractive index changes are causing the light to bend in different ways. So once again, you would have an adjustable lens here that compensates not only for the cover slip, but also for the material in which the sample is embedded. Now, it turns out that that's a characteristic of high-end dry lenses, that is non-oil immersion lenses. Because if you have an oil immersion lens, now the idea is that if this is now the oil lens, is that you put in a sort of a constant dollop of oil. And the refractive index of oil tends to match the refractive index of the glass, and the lenses are designed to compensate for what now becomes a fairly common correction. So you can just design those lenses one way. But if you're using one of these high resolution dry objective lenses, that's where the correction color becomes an important function. So that's all I wanted to cover today. Basically, the idea that although the achromatic lens as a concept had been developed in the mid-1800s, it wasn't really applied to microscopic lenses, lenses for microscopes, until the work of Lister in 1820s, 1830s, something like that. So that's the history that we've hit for this part of the lecture so far. Now, in the next couple of lectures, I want to talk about how these kinds of microscopes were applied mostly by people whose names you've heard, Schleiden and Schwann, to do studies that led to the formation, the development of the cell theory.